Anyone want to chime in with a guess? This is from the reading. Well, let me ask you this. What's this part? And that's your sample and hold, yes. And here's your voltage in, and this is your digital data. So what you have here is a successive approximation analog to digital converter. That's an up-down counter right there. This counts up or down. And this is a comparator, and what it does is it says if the output from the digital analog converter is too low, then count up. If it's too high, then count down. And what you want to do during the end of conversion cycle is sample the DAC input right in through here and put that into your microcontroller or whatever kind of computer you have. And then what you can do is you can find out what the voltage is by using this quantized and sampled representation of the voltage. This analog to digital converter is an essential part of what goes on when I speak to you through Zoom, because I'm using an analog microphone, and somewhere in that microphone is an analog to digital converter which gets my voice and puts it into a digital form so that it can be transmitted into your ears eventually. So that's a critical part of communication systems, of well, I could say recording systems, which are probably communication systems. All kinds of interesting and wonderful things are needed. Even the camera has to have an analog to digital converter in it, although its nature is somewhat different. So when you look at the answer, is it an analog to digital converter? The answer is yes. Is it a successive approximation analog to digital converter? And the answer is yes. Is it a device that gives 6 dB of signal to noise ratio per bit? And that's also true. So if you have 8 bits worth of DAC, it's going to give you something like 6 times 8 or 48 dB of signal to noise ratio, give or take 3 dB. And so the all of the above is a correct answer. And so that's how we get analog signals into digital computers. If it's an analog computer, we don't need this. But we're not doing analog computers in this class. We do digital design. So we care about digital computers. So now that we've done sort of the simple questions, let's get into some of the more complicated ones. Let's see. I'm going to go back into the chat here. Someone writes, can we do 7? Yes, we can. It's a little bit long, but let's have a look at it anyway, okay? So this is 7. I'm going to take this entire thing and I'm going to write it out on the paper here. So let's do that. So we got a present state. This phone has been ringing off the hook. We've got a next state, and for the next state it's going to be x equals 0, x equal 1, and then the output is going to have x equals 0 and x equal 1, and let's see. The states are numbered A through H. A, B, C, D, E, F, G, H. And then the next states are going to be HC, CD, HB. And outputs are going to be I think I got that right. That's the, and the question is, given the state transition table, choose the reduced state transition table that belongs to the new finite state machine using implication charts to minimize the number of states. So let's see if we can do minimization. State minimization. Is it a Moore machine or is it a Mealy machine? What could this be? Moore machine or Mealy machine? You got a 50-50 shot. What do you think it is? Moore or Mealy? Yes, it's a Mealy. And why is that? Well, because the outputs are a function of the inputs, not just the present state. Let's take a look at how we can do an implication table. B, C, D, E, F, G, H. And we'll do A through G. A, B, C, D, E, F, G. Okay. And now we'll do our lower triangular matrix. And now we want to compare outputs. Now, check it out. There are 2 columns worth of outputs. We've got to try them all. So we'll start with the left column, comparing against all combinations. Then we'll go move to the right column, comparing all combinations. You can't just use one column. You've got to do both. So we know A is different from B, C, D, E, and F. We know that B is different from G and H. We know C is different from G and H. And D must be different from G and H. And E is different from G and H. And F is different from G and H. Now we go to the next column, because G can't be different. Might be different from H, but we don't know. Let's look at A, and we see it is different from B and E. So I got B already, and E I got already. We see B is different from C, D, F, G, and H. C, D, F, G, and H. C is different from E. D is different from E. E is different from F, G, and H. And so now we got a lot of X's in there because we had to consider both columns. Both columns. So that's kind of an interesting problem, right? So let's take a look at some of these things we might be able to do a reduction on. Let's consider C and D. C and D is not true if H is not equal to F. H is not equal to F, therefore C is not equal to D. That's pretty good. Let's do another one. Let's try C and F. C and F is not true if H does not equal F. H does not equal F, so C does not equal F. D and F. D and F is true if F is equal to F. That sounds good. If G is equal to H, we don't know about that one. Let's see. Could G be equal to H? Maybe. Let's look. So G and H are true if G is equal to A and C is equal to C. So this requires G be equal to A. Is G equal to A? Well, here's G and there's A. G is equal to A if G is equal to H. Well, wait, we got G equals A if G equals H. So this G and A is true if G equals H. So G equals A if G equals H and if C equals C. So check it out. G equals A if G equals H, and G equals H if G equals A. So that's circular, right? So I know now that G is equal to H, and it looks like A is equal to G, and so that whole thing is equal to A. So that's pretty cool. I got a nice reduction there. What about that FD thing? I see GH is in there. So it says here F is equal to D if F equals F. That's good. And if G equals H, and it does, so that's cool. Now I got D equals F. So that's another nice reduction. So let's take a look at A and H. Well, we know those are equal, but we can check it just to be sure. A and H are true if A equals H and if C equals C. Oh yeah, A equals H. But we knew that already because of this. And then it says here, what about B and E? Yep, you got a question? Some questions? No? Okay. So how about B and E? We didn't do B and E yet. And B is going to be equal to E if C equals C. That sounds good. If D equals F, oh, D does equal F. So check it out. B equals E. So B equals E. That's cool. So what do we do? This part, right in through here, that's A. And anything that makes reference to it can be written as A. So anytime you see a G, that's A. Anytime you see an H, that's A. What about, changing colors now, what about D and F? We know we can cross out F and write in D. So that's pretty good. What about B and E? We can cross out E and, yeah.
Do you mind sliding on your paper so I can see what you're writing below?
Oh, can't see it. Oh, I'm sorry. Thought you could see it. Yeah, I'm looking at the paper and you're looking at the monitor and you're like, what? What's he drawing? Yeah, I'm going down through my list of things that are equivalent, and then I'm crossing out those things which are equivalent. I just crossed out E, and now I'm going to take B anywhere I see E and write in B, but I don't see it too many times. So what I'm left with now, so I'm crossing this out and substituting in A, is H should be an A, right, because A equals H. H should be an A. And now I have A, C, I got D, C, A, B, F. F should be a D. And I think I've gotten everything now. We've got a nice simplified form, and it looks like this. Let's write it out in its simplified fashion. It's going to look like A, C, 1, 0, B, C, D, 0, 1, C, A, B, 0, 0, D, D, A, 0, 0, and this is the output for X equals 0 and X equal 1, and this is the next state for X equals 0 and X equal 1, and that's the present state, and this is my reduced finite state machine. And now, I hope I got it right. Let's have a look. Which question is this? This is supposed to be homework 7, right? Yeah. Let's make sure I'm looking at the right thing. So it says here A, B, C, D. That looks good. AC, CD, AB, DA. Hey, look, I got the right answer. 1, 0, 0, 1, 0, 0, 0, 0. Yay, I have the correct answer. So that's how you get that. And that's how you do number 7. What do you think? Any questions about what I just did? That is a state minimization problem using implication charts. That's as complicated as problem I'd like to get. After that, After that, got to use computers or something. I don't know. Once it gets too big, it gets a little tedious and error prone. It says, can we do 7? Yes, we did 7. Can we go over 5, please? Yes, we can do 5. Are there any questions about this? Is problem number 7 here. We can just sort of write that. Number 7. Okay. Everybody good with number 7? Moving on to question 5. I'm going to splurge now and use a fresh piece of paper because we have a budget. So there. Let's try number 5. Number 5. For number 5. Okay. Here's number 5. It's a tricky question. Okay, here's number 5 as it's presented. Right? Without my annotations. Now I know that if this state 2 is leaving with a correctly labeled arc, that means there's a 1 coming out. I need a 0 coming out somewhere, and there's another arc going out, so that must be a 0. I also know that if this one has an arc going to itself with a 1, the one that's leaving must be a 0. Then I also know that this one has an arc going out that's a 1, therefore the other arc must be leaving as a 0. And in fact, every one of the outputs is going to be 0. It's not labeled properly. No doubt. This needed to be labeled properly. And in recognition of the fact that it is not labeled properly, you can look quickly at the eligible answers, and you will see that none of the above, the machine is not properly labeled, is a legitimate answer. Moreover, if you go through the exercise of minimization, you will not find the correct answer amongst the presented eligible answers, except for this answer. It's the only one that fits. So, sort of like, what's the question? Find the minimization thing. It's a trick question. You can't find the minimization because I didn't label it properly. Had I labeled it properly, you still wouldn't be able to find the minimized version of that particular state machine. Although, if you label it the way I showed you, you can. You can find the minimized form. You just won't find it as one of the selections underneath the problem. So I can work the minimized form for you if you need it, but other than that, I don't know. What do you think? Want to see that? Yeah, I can do that. You like that sort of thing? Do it for fun. Do it for fun. Do it for fun, Professor Lyon. Okay, I'll do it for fun. So if you're going to do it for fun, then what you want to do is you want to take that state diagram and you want to encode it into a present state, next state table. And the states are labeled state 0 through 6. And then state 0 transitions to state 1 or state 4. And you can see that right in through here. State 0 goes to state 1 or state 4. State 1 goes to state 2 or state 1. State 2 goes to state 1 or state 6. State 3 goes to state 1 or state 3. State 4 goes to state 5 or state 4. State 5 goes to state 1. No, state 2 or state 1. State 6 goes to state 5 or state 3. And then you need the outputs, which are going to be, looks like everything has a 0 on it, except for the transition from state 6 to state 3. And everything else is a 0. Am I right about that? I think that's right. This is the only one that has a 1 in the bottom. Everything else is a 0 on the bottom. And that's it. And so now, let's compare outputs. S0 is different from S6. S1, S2, S3, S4, and S5, all different from S6. Okay. Looks to me like we have to start doing comparisons. S0 is equal to S1 if 1 is equal to 2, and if 1 is equal to 4. Let's take a look at 1 and 2. 1 and 2 are true if 1 equals 2 and if 1 equals 6. 1 does not equal 6. Therefore, S0 cannot equal S1 because 1 does not equal 2. S0 gets compared with S2. And that's true if S4 equals S6, but it doesn't. We'll go to S0 and S3. S0 and S3. It's true if S1 equals S1 and if S4 equals S3. We don't know about that. So this is 4 and 3. Let's look at 4 and 3. S4 equals S3 if 1 equals 5. 1 equals 5. And if 4 equals 3. Let's see if 1 equals 5. S1 equals S5 if 2 equals 2 and 1 equals 1. So S1 does equal S5. That means S3 must equal S4 since S1 equals S5. What about S3 and 4? Yeah, that's good. And now what about S0 and S3? S0 and S3, S1 and S1, S3 and S4. We already decided that was equal. So this is equal. So now let's write out what we've just discovered. S0 is equal to S3. That's cool. S1 is equal to S5. Also cool. S3 is equal to S4. Now we've got a bunch of equality elements here. Let's take a look at S0 and S4. S0 equals S4. Well, we know it does from here, but let's just take a look anyway. It's true if S1 equals S5, and it does, so therefore S0 equals S4 if S4 equals S4, and it does, so S4 equals S0. S0 equals S5, it says here. Well, if that's true, then this comes up there. Let's see if S0 equals S5. And S1 has to equal S2? No, it does not. S1 equals S3. Let's see if that's true. S1 equals S2? Maybe. No, it doesn't. S1 equals S4. Let's look at that. S1 equals S5. Yes, it does. S4 equals S6. No, it doesn't. S2 equals S3 if S1 equals S1, and if S3 equals S6. It does not. S2 equals S4 if S1 equals S5, and it does. And if S4 equals S6, it doesn't. S2 is equal to S5 if S1 equals S5, and it does. And if S4 equals S6, it does not. So here comes S3 and S5. S3, S5 is true if S1 equals S2, and it does not do that. And then S4 is equal to S5 if S2 is equal to S5, and that is not true. So there you go. That's what we're left with. And so what that says to me is that if you see S5, you can cross it out and write S1. If you see S4 or S3, you can cross it out and write S0. And that'll be a minimized form, but it doesn't save you from the fact that your original diagram was not labeled properly. So if you knew how to label the diagram as I do, then you will get a correct answer. This is a minimal form. However, because it was not labeled correctly, your best answer is it's not labeled right. Go back and label your diagram properly, sir. It's very formal. So that's it. Let's see, what else? Can we do 6 next? Yes. Yes, we can. Number 6. What does number 6 look like? Okay, here's number 6. And that's a diagram that we're going to have to encode into a present state, next state table. How are we doing on time here? We got time. So what we're going to do, homework 12, number 6, right? We'll need a present state, and we're going to need a next state for x equals 0, x equals 1. We'll need an output, and the states are numbered 0 through 6. So I'm just going to write out 0, 1, 2, 3, 4, 5, and 6. And the next states are going to be 5, 2, 0, 0, 1, 1, 0, 5, 1, 0, 1, 1, 0, 5, 1, 0, 5, 1, 5, 4, 1. You know that row matching could take out these 3 things automatically, and you just be left with 1 right there. But let's do it sort of with the implication chart, just to sort of humor me. Is it a Moore machine or a Mealy machine? More machine or Mealy machine? That is a more machine because it has only a single output for each state. You can tell either by virtue of the present state next state table or by virtue of this diagram, which shows outputs are only a function of the state. So that's pretty good. Let's take a look at the implicant chart. Oops. Okay. Let's see now. Row 0 is different from all the other rows. 1, 2, 3, 4, 5, 6. And that's what I got. All the other ones have outputs that could, in theory, include them in the equivalence. So let's start doing comparisons. If you want to compare 1 to 2, you need to know if 1 is equal to 5. We don't know about 1 and 5, so let's compare it. 1 and 5 are equal if 1 and 5 are equal. Well, wait a minute. 1 and 5, 0 and 0, and 1 and 5. Yeah, so 1 and 5 is equal. So 1 is equal to 5. And let's look at 1 and 2 again. 1 and 2 are equal. And now let's take a look at 1 and 3. 1 and 3 are equal if, well, they are equal. So now that's equal to 3, getting a nice reduction. How about 1 and 4? They're equal if 1 equals 5, so 1 is equal to 4. Some reductions, huh? How about 1 and 6? 1 is equal to 6 if 0 equals 5. It does not. 2 is equal to 3 if 5 is equal to 1, and it is. So 2 equals 3, but we knew that already. 2 equals 4 if 5 equals 5, and that it does, but we know 2 equals 4. 2 equals 5 if, did I just do that? 2 equals 4 if, oh, it's the same. So they both, 2 equals 5, 2 equals 4. Then 2 equals 6 if 5 equals 4 and 0 equals 5. 0 does not equal 5. Let's look at state 3 and compare it to state 4. It's true if 1 equals 5, so that's good. 3 is equal to 4, and we got that anyway. How about 3 and 5? 3 and 5 are equal if 1 equals 5. We see 1 does equal 5. If we go 1 and 5, we get a check mark. So we've got 3 and 5, but that's already in there. How about 3 and 6? 3 and 6 are equal if 0 equals 5. It does not. 4 and 5 are equal. Well, they're just equal. And you can tell they're equal because of the equivalencies here. How about 4 and 6? 0 and 5 are not equal. How about 5 and 6? 5 and 6 are not equal because 0 and 5 is not equal. And that's how you do that. By the time you're done, you're crossing off 2, 3, 4, and 5. And replacing the whole shebang with a 1. And now you're down to just 3 states, 0, 1, and 6. None of the above is the correct answer, but it takes a bit of work to find it because all of these other answers have way too many states compared with a truly minimal form. So none of the above is a good answer for question number 6. Any other questions about homework 12? Let me just scroll back through the chat here and see if there's any other questions that haven't been answered. It looks like I got them all, huh? No more questions? Question 2. No, we did question 2. We did questions 1, 2, and 3, and I think we finished question 4. Question 2? Tell me we didn't do question 2. I got it recorded for my... We didn't finish 4. Okay, that's fair. Yeah, if you have access to the homework, I'm sorry, the recordings, you can just go in and watch what we did last time. It's on my web page at normally I put this over here. Here. Yep. See, if you go to my web page over here, you'll find all the recordings. Because I record this stuff. I'm even recording this right now because I'm a nice guy. And also because I have your mind in mind. So we didn't finish question 4. That sounds right. Let's take a look at it. Question 4. Oh, yeah. Yeah. I remember this now. All right. Why didn't we finish question 4? Well, because question 4 is a honkin' big question. That's a big question. And that's why we didn't finish it. It just takes longer. That's all. It's not like we were being obstinate or anything. Shoot. Well, you know what you want to do. This is a case where neatness counts. So I'm going to have to redraw the whole darn thing. No doubt. Maybe we could do something where we have the present state. This is number 4. I'll just write that there. Then we'll have the next state with x equals 0 and x equal 1. And then we're going to have an output. And we're going to, it's A through K. This is a large one. Okay. Here we go. A, B, C, D, E, F, G, H, okay. It's 0, 0, 0, 1, 1, 1, 1, 0. And then comes the output. So much for being neat. You know what? I think we can be neat. Let's be neat. Because what the hey? Let's make it nice. And then the output comes out over here. And I think what I'll do is I'll just kind of draw a horizontal line every now and then. Maybe every two rows, just to keep things lined up nicely. There, that looks better. So, yeah. So this is going to be BICG. 0. BCFG, 0. HDDF, 1. HCEG, 1. BCIG, 0. BIIK, no, FIIK, 0. In fact, everything's going to be 0 except for the last row, which is a 1 on output. And now I have JKGH, EFCG, nope, yeah, that's right, B, F, C, G, and A, C, E, G. All right, I think I got that right. Check me, just in case. So that's supposed to be for input 00, 01, 11, and 10. This is numbered in gray code. That's okay. We'll start with B and go to K. And now we're going to start with A and go to J. Now we'll build the lower triangular matrix. So you know what you could do, if you really wanted to do it upright, is put the lower limit first, and then oh, this is too much of a pain. Okay. Did I do that right? Anybody see any errors? Where are you recording exactly? I'm recording on my web page, right here. You go to this web page, and you go to where it says courseware and courses, and you go to the course number CR245 Digital Design 1. And then you can see the list of recordings, and it's all there. Everything we've been doing, it's all there. Let's see. I don't want to switch from the camera to the desktop, because if I do, it's going to mess things up. But toward the end, I can do it, just so long as I don't have to try and go back to the camera, because if I do that, I'm pretty sure it'll just mess everything up. Besides, I'm in the middle of the problem, so switching video inputs is hard. Well, it's not hard, it's just it never seems to work right for whatever reason. I don't understand. I think it's a contention issue, put it that way, contention issue. So let's do the output comparisons now. A is different from C, D, and K. B is different from C, D, and K. C is different from E, F, G, H, I, J. D is different from E, F, G, H, I, J. E is different from K. F is different from K. In fact, F, G, H, I, and J are all different from K. And that eliminates many of the squares. Now let's compare A and B. A and B are true if B equals B, and it does. If C equals I, it does not. Let's see now. A equals E requires that B equal B and C equals I, but that doesn't work. A equals F if B equals F, and if I equals I and if C equals I, that doesn't work because C doesn't equal I. A equals G if B equals J, and if K equals I. K does not equal I, so that's no good. A equals H. A equals H if B equals E, and if I equals F, and if C equals C. So I need I to equal F and B to equal E. Let's take a look at B and E. B equals E if B equals B and C equals C, and I equals F. So again, I equals F. Now, let's take a look at IF. I equals F if I equals F, that's good. If I equals I equals I. If D equals K. D equals K, let's keep going. D equals K if A equals H, so that's circular, right? And if C equals C and E equals E and G equals, so this is A equals H. So A equals H if I equals F, and I equals F if D equals K, and D equals K if A equals H. So it looks like if I can get B to equal E with I equal to F, then that's equal, and that's equal, and D equals K, that's equal. So now what do we got? I got B is equal to E. That's this. I got A is equal to H. That's this. I got F is equal to I. That's this. I got B is equal to E. I got that. I got A equals H. Got that. Got F equals I. Got that. So I got a few things already. D equals K. So that's another one. So I got a few. Let's look at this one, A and I. Well, now if A and I are equal, then I can make an equation on all of that. Let's look at A and I. That's going to be true if B equals I. A and I. If I equals I. If I equals C. Does I equal C? No. So A does not equal I. How about A and J? A equals J if B equals B. If I equals F, it does. C equals C. It looks like A equals J. So now I got, does B equal F? So with B and F, I got to have B and F, which is good, C and I, which is no good. I got to do B and G, I got to have B and J. Maybe that'll work. So for B and G, B and J, C and K, That's not too bad. C and K. So B and G needs C and K, F and G and H. G and H. So these a bunch of interesting things. Let's look at some of this stuff. How about G and H? That's for I and E. Isn't that right? Let's just make sure. Yeah. No, that's J and E. J and E. So let's look at J and E. J and E, we don't know. K and F. Let's see. K and F is no good. So that means G does not equal I because, let's see, did we do this right? K does not equal I. Right, there's K and I. Here's G and I. So G and I don't equal. And so what were we doing? B and H? B and H depends on B and E, which is equal. C and F, which is not equal. B and I depend on B and I. C and I, which is not equal. B and J depend on B and B. C and F. C and F is not equal, so that's not equal. Let's see. CK depends on AH, which is good. CD, we don't know about that. That's CD. C and K depends on C and D. D and E. No, D and E are no good. Let's look at C and D. H and H, C and D. D and E is no good, right? Because D and E. How about E and F? E and F needs B and F. B and F is no good. How about E and G? E and G is BJ. BJ has got an X, so that's got an X. EH. EH is EBE. BE's got a check mark. CF. Well, CF has got an X. How about EH? I'm sorry, EI. EI. It requires BI. That's got an X. How about EJ? EJ. That's BB. There's CF. CF has got an X, so that's going to have an X. FG. FG needs FJ. FJ, we don't know. So now FG needs FJ. IK, that's got an X. FH needs FE. That's got an X. FJ needs BF, and BF has got an X. GH is JE, and JE has got an X. GJ is BJ, and BJ's got an X. HI is EI, which has got an X. HJ is BE, which is FFCCD. BE looks all right. B equals E, so that's okay. And now what about, so that says H equals J, but we got that already. And then how about I equals J? I, here's J, here's I. Yes, if B equals I, B does not equal I, so then this gets an X. And that's all I got. That's what I got for this one. So there's a compelling argument that you can remove E, and everywhere you see E, you can write in a B. you can remove K. And everywhere you see K, you can write in a D. You can remove I, and everywhere you see I, you can put in an F. You can remove H, and everywhere you see H or J, you can put in an A. Wow, there's a lot of reduction there. So that was question number 5. No. Was that question 5? I'm sorry, we were doing question 4. Yeah, question 4. So question 4 says the answer should be in the form A, B, C, D, E, F, G. What do I got here? A, B, C, D. B was equal to E, F, G. Oh no, there's no E. Yep, I'm right. Because look, there it is. A, B, C, D, F, G. It skips E. And then it says I is equal to F over in here, so that should have been an F. And so then, when you look at the answer, it should say BFCG, BF, BFCG. Then it should say BCFG, ADDF, ACEG, E is equal to B, FFFD. That's right. And then this says JKG, but J is equal to A, and K is equal to D. So that would be DDG and A, which is ADGA. Here's GA, and that's supposed to be an A. J is A. Yeah, so that's an A. So that's correct. It's a little sloppy, but there it is. It worked. So what do you think of that? Question 4. Good, right? So now, shall we explore the web and show you exactly where all of this good stuff is being recorded? Is that a sensible thing? Because that's what I do. I stop this stuff.